Yeah, hello. Thank you for the opportunity to speak here today. I would like to start with a classical Turan-Kobilius inequality from number theory. On the screen, you can see it here formulated for strongly additive arithmetic functions. And the main goal of the inequality is to bound the variance of specific number theoretic functions by the variances of its components here. So long ago, in '85, it was proven that the scalar C is actually 3/2 plus a remainder term. No, this is it's formulated for strongly additive arithmetic functions here. For only additive arithmetic functions, it would be different. But this is not the point of the talk. It's just an illustration. Yeah, and later on, it was even proven that this remainder term is negative. Yeah, and the goal of the talk is to give a quick overview of what has happened for similar functions defined on combinatorial objects. So we begin with very well-known things, that is the symmetric group of degree n. And similarly to natural numbers, every permutation can be decomposed into a product of disjoint cycles. Yeah, sure. Okay. Yeah, and then we can define a structural vector, which is the number of cycles of the degree j. So the jth coordinate of the structural vector would be the number of cycles of the degree j. So this example here, the coordinate vector would be 1, 1, 1, 0, 0, 0. Now we add a probabilistic element to the system. At the beginning, we assume that all permutations are sampled uniformly. Then I would like to mention also a very well-known fact from random permutation theory, that is a random structural vector has the same distribution as the conditional distribution of this vector C, which is comprised of independent random variables with parameters 1 over j. So from this, we can draw a conclusion that the structural vector is asymptotically Poisson random is distributed as the jth coordinate of the random structural vector is distributed as a Poisson random variable as n goes to infinity. Yeah, and using this fact, we can and some technical knowledge, we can compute the covariance of the coordinates of random structural vector. And we get this expression. As you can see here, the coordinates are independent if both of these conditions do not hold. Now we can start talking about functions that are defined on permutations. So a first function class we will call completely additive, and it will be functions that can be expressed as a linear combination of the random structural vector. So if we were to look at traditional number theory, then those functions would be additive arithmetic functions. Mhm. It is quite easy to compute the variance of such functions, and it is comprised of two quadratic forms. The first B is the sum of variances of the functions H components, and then the second term it appears due to the dependence between random structural vector coordinates. And in 2018, it was proven that we can bound the variance of such function classes by its first term and by the constant 3/2, which is the same as for the number theoretical functions. If we were to sample instead of uniformly, but to use a Ewan's probability measure, which is used in some genetic modeling using permutations, then we can generalize the results shown in the previous slide, and instead the variance can be bound by the first term in the following way. Why do I call it this a generalization? If we choose theta equal to 1, then we arrive at the same at the result that we saw previously. Now let's define another function class on permutations. We will call such functions strongly additive if they can be expressed as a linear combination of indicator functions that show whether the permutation has a cycle of length j. So if we once again look at the parallel with number theory, then those functions would be called strongly additive arithmetic functions. Yeah, the same problem for strongly additive arithmetic functions is much more complex and much harder than for completely additive functions. You can see that from the fact that the covariances of the truncated variables or truncated values of a random structural vector are correlated for the places where previously for completely additive functions they were not, and the covariance expression becomes much more complex. For variance, it is the same. It is, instead of being comprised of two quadratic forms, we have now four. We will not look at the last form because it is always strictly negative, but we need to evaluate these quadratic forms delta 1 and delta 2 to obtain our result. Yeah, and that is exactly what we have done. This is a brand new result from this year. We have shown that for a strongly additive function, we also have the same constant of 3/2 that is binding the variance, but differently from completely additive functions, we have a remainder term which is not improvable. A proof sketch. So the idea is, first of all, to perform a variable change for the quadratic forms delta 1 and delta 2 in such a way that the leading term of the variance, that is the form d, would reduce to the Euclidean norm. Afterwards, the problem reduces to examination of the matrix Q. In fact, it is enough to find the minimal value, the minimal eigenvalue of the matrix Q to prove our claim. And that is what we do. We use lemma 3, which is a well-known linear algebra fact. So for any matrix M, we can choose vector x and a scalar value a, and this inequality will hold here. So instead of M, we plug in Q, and we want to find, we want to make a very good guess for A and X. A, in this case, we want to choose as a -1/2, which we believe to be the smallest eigenvalue, and X, a guess for its corresponding eigenvector. In that case, this right-hand side of the inequality becomes very, very small, and we can say that the matrix M has an eigenvalue in the vicinity of A. Yep, I will skip the proof part, the technicalities. Yeah, and there still is an open problem for strongly additive functions. Computer calculations show that the variance bounded by the first term is actual, that the remainder term is accurate, but it is negative. And we have still not shown that. So the inequality can be even sharper. That's it. Thank you for your attention.
Thank you very much. Question?
Thanks. Can you discuss briefly the usefulness of these bounds on upper bounds on the variance of the various functions?
Yeah, so similarly to number theory, these bounds are used later in proving a couple of useful facts. One of those would be a central limiting theorem for involving those functions.
Further questions?
So many properties of uniform distribution can be extended to Ewens distribution. And here you discussed the variance. I was wondering, like, what about higher moments or characteristic functions, such things? Do you have any expectations on what might?
No, this the research that we are looking on is strictly the variance and binding the variance with the sum of variances of the function's components. So we're not looking into that.
Further questions?